In this quick tip, I'd like to talk about the VDB Extrapolate node. And I also want to use this as an opportunity to show you guys what you can expect if you check out various node Bible entries. So for this one, I'm going to go through each one of these parameters one by one and tell you what everything is doing. So allow me to start with why you might want to use this node. This is brand new to Houdini 19, and the documentation says this node extrapolates sign distance fields stored as VDB volumes. Optionally, extrapolation can be masked with other VDBs so that the new distances are computed only where the mask is active. To translate all that, this node is something that you want to use if you're trying to modify an Sdf volume in some sort of way. So if you're not sure what Sdf volume is, do check out Houdini for the new artist too, because I define that much better. But basically put, what we're doing is we're figuring out the surface of Craig right here, and we're trying to assign that surface with the value of 0 and measure the distance away from that value of 0. So if I do a volume slice here, we could see that our values are going to be positive if we, let's say, take this narrow band outwards away from the mesh and negative as it goes inside. To make a marker for this, we can actually see those values by zooming in. We have a value of 0 at the surface, and once we start going inside the mesh, it turns negative. So in practice, this gets used for all kinds of different things, but the main thing to know with an Sdf volume or a distance VDB, same thing, is that we're trying to measure a distance away from the surface. Also, key to understanding this is understanding what a narrow band is. And so if you're not familiar with that, a narrow band is going to be the area that is being measured. We'll notice that right now we're measuring out away from the surface, and then it caps out at 0.08. That's because with the exterior band voxels, we're only measuring 5 voxels out. Or we can use world units by turning this on, and this is going to be in meters for how far out it measures things until it caps out at a value of 0.2, let's say. Again, if those concepts are new to you, please check out the Node Bible, specifically the VDB from Polygon's entry, along with Houdini for the new artist too, because that'll help things out. Anyway, assuming that you know all that, the VDB Extrapolate is here to redefine that narrow band and modify the Sdf volume in some kind of way. So the default operation is to expand the Sdf narrowband. If we go set a visualization down here, a volume slice. So let's do that again. And we go ahead and just move this right there. Turning up the dilation is going to expand that measurement outwards. And so let's press D for display, see what's happening to these values as we expand. So if we zoom in here, this is inside the mesh. Let's template Craig real quick so that we can see where that's landing. Outside the mesh is out here, and we are measuring further and further out as we turn up the dilation. That dilation goes in all directions, so it measures further inside the mesh as well as outside. And if we go down to the dilation pattern, we have 3 options: faces, faces and edges, and faces, edges, and vertices. As we can see in the docs, this just changes the algorithm. Faces is the fastest, faces, edges, and vertices is the slowest, but can produce the best results for large dilations. Faces and edges is intermediates in terms of speed and quality. So in other words, the more components here that you add, the more accurate this operation is going to be, but it's also going to be slower. So up to you which one works for your situation. Lastly, we have the iterations, which in this particular algorithm isn't going to do much for you. Oftentimes, you only need 1 iteration to have accurate results, and so only turn this up if you're noticing a difference in quality for whatever operation we pick up here. Last but not least, for this mode, we have the domain direction, which by default is all directions, so both inside the mesh and outside the mesh, but you can say which direction you like by specifying that right here. If you have multiple volumes coming in the first input, we can always specify that up here in the source group as well. So if I say surface, it's going to say that the primitive name attribute is equal to surface. middle mouse, there it is, right there. Next up, we have expand SDF into Mask Sdf. So we don't have a mask yet, which is why it's upset. That's why it's yelling at me. So what if we have a sphere? Let's just say labs sphere generator for right now. VDB from polygons, turn that into a distance VDB or an SDF. And we move that up so that it's intersecting with Craig's shoulder. Well, let's plug that in. Here's our Mask Vdb. It's upset because the mask grid does not have the same transform as the fast sweeping grid surface. So what the heck does that mean? It means that our voxel size doesn't match. So when it says the transform, it's saying how big the voxel is. So 0.02 right now is our first input. Our second input is 0.1. That's why it doesn't like it. That's why it's not working. So we can change this to 0.02, or we can just tell our VDB from polygons to always listen to this resolution by plugging that into the second inputs. Now, this guy is going to be 0.02, as we can see, and this now works. So what actually happened when we expanded the SDF into Mask Sdf? Let's go here, see if we can figure that out. So here are the values that we have. It looks like if we turn our marker on, these values inside the sphere are basically being measured away from Craig's surface. So in other words, when the SDF goes to create that band, that area of measurement, we can specify which area it should measure out to with this SDF volume. We have a sphere that's telling the band along Craig to measure out in the areas which intersect with the sphere. Hence, expand SDF into Mask Sdf. We're defining where to measure out from the narrow band. For most situations, you can leave this ignore active tiles unchecked. This especially is true if you're masking with SDF volumes. According to the docs, this option should normally be disabled. But note that active tiles, which are sparsely represented regions of constant value, will, in that case, be densified. I'm not really sure what they mean by densified, honestly. But that could significantly increase the memory usage, and if you're using a proper SDF, then you don't have active tiles anyway. So it all goes to say that for most situations, you want to leave that off. But for some reason, if you find a use for it, then it's there in case you need it, I guess. Also, if we go up here to this Mask Vdb, we can specify a group for that second context geometry. If you have multiple SDF fields and you want to isolate one particular field, just like it is for the source group. Anyway, that about does it for the second operation. Let's see what the convert Fog Vdb to SDF does. So let's take a Fog Vdb called density and we bring it down here. Now, I'm going to turn off this template so that we can see what's going on. It looks like it created some sort of SDF volume based off of this fog ISO value. So if we turn up the iterations, this doesn't seem to really do much at all. With the fog ISO value, that's asking you what density value should be considered the surface of the mesh. So if we go to here and we do a volume slice of this guy, we can see that we have density values ranging from 1 to about 0. If we say 0.5 on the fog ISO, that's saying, okay, that's where the surface of the mesh is, which right now is about where the green is. So that's why this looks really funky. If we can take this to a smaller value though, like 0.01, then as you can see, this is much closer towards the surface. It's probably better to give ourselves a bit more than 0.01. So let's say 0.025 as an example. And if we go here to our volume slice, this is what we get. So here's that ISO surface. Let's go ahead and turn back our visualizer. And if we zoom in, we have negative values inside the mesh and positive values outside. Do keep in mind though that you'll probably have to dilate the area of measurement. And so we don't really have that option right here. If you want to use that way of converting, then I would also recommend going here and expanding that measurement outwards away from the surface. So that way we actually have a more proper measurement away from there, because this again doesn't have a very big narrowband region. But that could be nice if you're trying to save on memory, because the further you expand outwards in your measurements, the more voxel values are being used to determine where things are being measured from. So middle mouse here, we have 3.6 megabytes. If we go up 1, that's only 1.7. So this might be a very efficient way of converting a fog to an SDF without a large narrowband. This renormalized SDF is pretty cool because this actually changes where the value of 0 happens. If we go and turn up the SDF ISO value, we can see that this will actually change where 0 happens, essentially. And so that's different from the expand SDF because this is just expanding the area for measurement. The value of 0 doesn't change. Where it considers the surface to be isn't any different. However, this will actually change where that happens, like that. And the nice thing about this operation is that this is a lot more efficient than doing a reshape SDF. On a technical note, you might want to use this if you're trying to expand the SDF of a really heavy voxel mesh, or a voxel object, I should say. Because when you take the exterior and interior band voxels, what you can do is specify exactly where that narrow band is and only, let's say, expand in those directions. So we could see what the performance is, generally speaking, around here. It's pretty good. Compare that to the reshape VDB SDF, and this guy is not going to be as efficient because of the fact that it's going inside the mesh as well. So for those of you who have to deal with huge, heavy amounts of data, this is a really cool feature because that'll save you time and optimize the process. The last two parameters, the extend fields off of Fog and SDF, are, in my opinion, pretty confusing and poorly documented. So it's kind of difficult to see what this does, but other than trying to just perhaps experiment and see what happens. Let's first of all read the user docs here. The extend fields off of Fog Vdb says this. It's going to compute the extension of several attributes off a fog volume. Okay, so we have a fog volume coming in, we assume that. The attributes are defined by VDB grids that will be sampled on the ISO surface of a fog volume. Okay, so attributes are defined by the VDB grid that is sampled on the ISO surface of a fog volume. So if we go up here to our fog volume as an example, we have this interior band. And if we look at what that does to the values right here, if we go to, let's say, preview this, we can see that as we turn up the interior band, we're essentially feathering out that value of 1 closer and closer towards the center. So when it talks about sampling attributes at the ISO surface of a fog volume, I'm assuming that we are talking about this band right here. And these attributes need to be defined by the source group. So the attributes that are going to be sampled are going to be part of source group. So let's say that for right now we have this fog volume. Let's call it fog. Just copy that. And we will paste that into the source group right here. So there's fog. Okay, what else does this say? It says the attributes are defined by the extension group parameters. And so this is kind of where things get a little bit weird. We have this extension group, okay? And so it says the attributes are defined by VDB grids that are sampled in the source group, and then the attributes are defined by the extension group parameter. So it says two things which don't line up. It says the attributes are defined by extension group, and it says the attributes are defined by VDB grids that are sampled along the ISO value of a fog volume defined in the source group. So that's why the documentation isn't very good. It's not clear as to what the attributes are defined by. So anyway, if we have separate attributes that are defined in the extension group parameter, this mode only uses the first fog grid specified in the source group parameter. So yeah, again, the only way we're going to figure this out is by trying to play around with different setups and seeing what happens. We have a Fog VDB that's called test sphere, density right now. If we take a volume slice of that, we have a fair bit of ISO value or a fair bit of narrow band happening right there. And so that's going to merge in with this stream. So let's actually take this guy, that guy, make a merge and plug that in so that we have two volumes. We have the sphere and then we have our fog with Craig. So we define the fog up here. Let's go and say that this is fog, name is equal to fog. And then what happens when we set the extension group to the test sphere? Let's do a volume slice again. And right away, if we have our fog volume, that seems to be no different than what we had up here. If we have our test sphere, however, we have this guy versus this guy. So to me, what this is saying is that it's kind of like a Boolean operation that's happening here. And it looks at this ISO value somehow, and it figures out how to draw out this ISO value depending on what we set right here. It's difficult to say exactly how that works, but yeah, it's kind of like a Boolean with an extra control here on the fog ISO value that somehow blends into the ISO value along our fog. That's the best I can tell with what's happening right here. So anyway, that's that. If we reverse this whole thing, so let's say that, you know, this is our source group and our extension group is going to be Craig, which is the fog right there. We have a different looking result now for Craig. So there's the fog, and it looks like his ISO value kind of just stretches out towards the center. So again, I'm not entirely sure how to think of this other than the fact that it's like a Boolean of some kind, and somehow it blends the ISO values. You know, I don't think there's a really great explanation, so you'll just have to play with this to see what happens. To make matters even more confusing, we have this convert Fog Vdb to Sdf, which converts a scalar fog volume into a signed distance grid. Active input voxels with scalar values above the given ISO value will have a negative distance values on outputs, i.e. they will be assumed to be inside the ISO surface. So if I click this on, we have something weird right here where I think we're going negative on the inside of Craig now. And if we try to bring this back to our sphere, it doesn't look like there's any difference. So again, I'm not entirely sure what's going on here. It says also that extending the test sphere density grid using fog grid. Yeah, so you know, your guess is as good as mine on this. Play around with this, see if you can get something that works, but otherwise I would avoid it. Now, if we use this extend fields off of Sdf, I do find that this is a bit more predictable as to what the behavior is supposed to be. What I have right now is Craig as an Sdf as well as our sphere. They get brought together and we end up with this. So in the volume slice, let's go ahead and isolate our sphere, our test sphere. It looks like it made an Sdf volume out of that, D for display, and the values here are in fact going negative along here by 0.04, and they're measuring out by a certain amount from the ISO value. What's determining how far this measures out, I think, might be where the ISO values intersect somehow, but it's hard to be sure exactly how that's working. So anyway, visually speaking, it kind of gives you this weird armband around Craig wherever things intersect. And if you want to change the distance of that armband, you can go ahead and just change the exterior voxels and expand the narrow band along Craig. We can also do the same thing with the fog. So here I've set the sphere to a fog, and now his armband is a, you know, it's a fog sort of thing. So if we go now to, I believe it's the test sphere, we end up with this. So again, not entirely sure how to think of this, but if you can find a cool way of using this in your production, if you can find a cool way of you know, making this work for you, then great. I personally, though, avoid it in production because it's not explained very well and it's difficult to use. So, in practice, what I find with this VDB Extrapolate is that this might be a really great way to convert a fog to VDB efficiently. It's a great way to expand the narrowband if you need to, and it's a really good way to change where the zero value is along the SDF. Besides that, though, I wouldn't use the VDB Extrapolate for anything else in production. All right, well, that about does it. I hope that you've enjoyed this quick tip, and for more information about VDB nodes, check out the Node Bible. Thanks for watching and have a good day.